Hello, everyone! In today's lesson, we'll take slopes of tangent lines even further by learning about derivatives and how they can be useful in real life. Let's get into it! In the last lesson, you learned how limits can be used to turn a secant line into a tangent line. But what if we're using the slope of the tangent line for something other than actually drawing a tangent line? In most cases, we call this process finding the derivative. This is the most common term because it doesn't rely on specific context. The derivative can be used for a lot of different purposes, including finding the slope of a tangent line. We can denote the derivative at a point using this notation, which would be read as f prime of a, or as the derivative of f at a. Luckily, we already know how to find the derivative. It's the same as the slope of the tangent line. This formula is fine to use if we want, but let's make a slight tweak here that will make the calculations a little easier. Let's also put the other point in terms of a. How could we denote an x value that is based on a, but is not in the exact same place as a? By adding some arbitrary amount to a. This h can be interpreted as the difference between the x values. You'll remember that in the slope formula, the denominator represents the difference between x values, so it makes sense that we could simplify it to just h. Finally, the limit requires one value to approach another. Remember, we want to move a plus h infinitely close to a. How would the limit help us do that? Moving the points closer together means making the difference, h, smaller and smaller, so we want to find the limit as h approaches 0. This is the formula we'll use to find the derivative at a specific point on a curve, the limit of the slope formula, where the distance between 2 points approaches 0. Let's try an example. We want to find the derivative of this function when x is 1. Just for reference, here's the graph of the function. What inferences can we make right away about the derivative at this point? We can tell right away that it seems to have a very steep negative slope here, so I'd estimate a slope of -5 maybe? Let's calculate the derivative and see how close our guess is. Here's the formula for the derivative at a point, specifically the point where x is 1. We fill in the function twice, evaluated at 1 and at h away from 1. Now we need to simplify as much as possible, being very careful when expanding powers and distributing negatives. Pause and do that now. Make sure to check your work against mine to see whether you made any mistakes. In the end, you'll be left with only terms with h's in them, so we can cancel one h from each term on top with the h in the denominator. The final step is to perform direct substitution, and we get a derivative of -6. Our estimate of -5 was actually pretty close. Try it yourself. Try working out these derivatives on your own, then come back for the answers. Let's check out how you did. For number 1, the function has 2 x's, so make sure to substitute 3 plus h in both of those spots. Then we simplify down to just h's, let the h's cancel, and use direct substitution. The derivative of f at 3 is 4, meaning the function has a slope of 4 when x is 3. For number 2, the setup is a little quicker, since there's only one term in the function. Then we need to expand this binomial to the 4th power and clean it up a bit. We reach a point where the h's will cancel, and then we can use direct substitution to find that g prime of 1 equals 4. Number 3 is a little tougher because of the square root. After we set it up, we need to find a way to manipulate it so the h in the denominator will cancel. What methods could we try? One approach here is to first rationalize the numerator. It isn't immediately obvious why this works, so let's keep going by combining the fractions in the numerator. After we combine those fractions and simplify, we get just negative h on the top numerator. Now you see where this is going, right? We can rewrite the division as multiplication by the reciprocal, and these h's will cancel. We're still left with a long denominator, but now that we're clear to use direct substitution, we can substitute 0 for all the h's and find that when x is 4, the derivative of k is negative 1/16. Note that math is often flexible. There are many ways you could have manipulated this limit. As long as your method brought you to the same result, negative 1/16, then you still did it right. Derivatives can also be used to calculate how quickly a value is changing at a specific point. This rate of change at a particular instant is known as the instantaneous rate of change. Just like how the slope of a tangent line is related to the slope of a secant line through the use of limits, instantaneous rates of change are related to limits of average rates of change. Take the average rate of change between 2 points along a curve, then find the limit as one point approaches the other, and you can find how quickly the value was changing at that one specific point. For instance, this function, Mia, what are you doing? Aw, Mia, are you okay? Oh, thank goodness. This function, h of t, models the height of Mia's rocket in meters, t seconds after launch. Back when we could only find the slope between 2 points, the only velocity we could calculate was the average velocity. But now that we have derivatives, we can find the rocket's exact velocity at any point we want. Pause and try to find the derivative 5 seconds after Mia took off. First, we set up the h limit with 5 as our determined x value. Expand 5 plus h squared. Distribute. Combine terms. Then use the h in the denominator to cancel an h from each term on top. Now use direct substitution, and we get an answer of 51. But what does that mean? We know it means that the slope of the tangent line is 51, but what does that mean in the context of this problem? Remember, the derivative indicates the speed at which something is changing at a given instant. In this case, the speed at which the rocket's height was changing at the 5-second mark. This answer means that 5 seconds after launch, Mia's rocket was still zooming upward at 51 meters per second. Let's find out how fast the rocket was going at a couple more points. Pause the video and find the velocity 11 seconds after launch, and at the moment it crashed back into the ground. After 11 seconds, Mia's rocket had a velocity of negative 7.8 meters per second. Why is it negative? If we took a look at the graph, the rocket reached its highest point at about 10 seconds. So at 11 seconds, the rocket must have been falling. The velocity is negative here because the rocket was no longer moving up, it was moving down. What about this second question? This one takes a little more work since we weren't given the x value, but it's not difficult to find. After all, when the rocket hits the ground, its height is 0, so we just need to find where the function equals 0. Do you remember how to do that? Factor the function, then find where each factor is equal to 0. This factor is 0 when t equals 0, but that doesn't tell us much. That just means that the rocket was already on the ground at the moment it launched. But this other factor is 0 when t is 20.4, meaning 20.4 seconds after launching, the rocket was back on the ground. Now that we've found that point, we just need to find the derivative there. Take a moment to calculate this derivative if you need to. H prime at 20.4 seconds is equal to negative 99.9 meters per second. In other words, when Mia crashed, her rocket was flying at almost 100 meters per second. She's lucky she didn't get hurt. Derivatives can be used to find the instantaneous rate of change of basically any real-life scenario. We can find how quickly objects are moving, how quickly a population is growing or decaying, or how well a company is doing. Derivatives are used for all sorts of things. Great work! Let's take a look at our key takeaways for today. Today you learned that the slope of the tangent line has a few other names, including derivative and instantaneous rate of change. We can calculate the derivative at a point on a curve by finding the limit of the slope as the difference between two x values shrinks to 0. Finally, we learned how derivatives can be used in a huge variety of real-world scenarios. With so many uses, it can get tedious carrying out these calculations at every individual point of interest. Which is why, in the next lesson, you'll learn how to use derivatives to analyze entire functions at once. Now that you're done with the guided notes, check out the lesson activity for more examples of how derivatives can be used, and then finish this lesson by completing the online practice. See you next time!
Hey, hey.